of an exponentiated F-test for one way or another in the presence of the outlier. I did it under the watchful eyes of my supervisor, as well as Dr. Oi Shitu and Dr. Angela Shuku. Yes, I'll be guided by this outline. Abstract, introduction to reference. These were abstract, then introduction. Yeah, the classical F-test to compare the means of populations greater than 2 rely on some assumptions. Assumptions which include constant error variance, independence of the population, absence of outliers, among others. Now, if any of these assumptions is violated, we discover that F-test will take invalid decision, as pointed out by Fisher Ronald in 1925. When we started this work, we asked ourselves the question, have there been any intervention to solve this problem? Now, we're able to trace the intervention to Welsh in 1951, from Smith in 1971, up to Chris Motin in 2007. All these people, they tried to solve the problem when there is assumptions violation. But the problem they had is that their counter is that they still have their type 1 error inflated even after developing a new robust F-test. So when we look at it critically, we discover that they fail. Why they fail is that they did not address the model of violation. What do we call model of violation? That is outlier. According to Becker in 1952, outlier is an observation, that is not consistent with the rest. So the moment it is present in the data cell, it will cause problem of heteroscedasticity and so on like that. Now the interest is testing this equation 1. That is one way ANOVA, where you are testing for effect of treatment. Then the outlier I just discussed, using for outliers, effect of removing it is there. Now, initially, when there is an outlier in the data set, what some people do is they discard. But the one they can discard is the one that is through erroneous imputation. Because at times, outlier could be a genuine observation. So how can we handle a stubborn data, a genuine, an outlier in the data set, and that is exactly what we want to do here. What we are attempted to do is to develop a model, a robust model that can accommodate outlier. So what happens if you violate assumption? I think I've stated all this. Then the possible way out, transformation, non-parametric, that people have done in the past. Now, equation 2 is telling us that if we actually want to improve on the conventional F-test, what we need to do is to improve on M and the degree of freedom for error. In the case of the conventional F-test, M is equal to 1. With M equal to 1, you are back at the conventional F. Now, these are the possible alternatives if your data violates one way or another. Then like that, I think I will quickly go to okay. Our aim and objective here. If you look at objective number 1, we actually want to develop a robust method that can handle outlier. And we are proposing about 4, because at the beginning of the research, we propose 4 and we choose 1 at the end of the day, and the one we'll be focusing on will be exponentiated F. Then, one of the problems faced by people that have intervened before now is that when they develop a robust F-test, they still use the conventional F-test. So what we intend to do, what we did, was that we curated a new distribution by modifying the conventional one. And when you create a new distribution, then you have to obtain all those properties, like the moment generating function hazard up to the entropy. Then we estimate parameters. Then we develop a generalized statistic for testing the equality of mean when there is a violation of assumption. These are the intervention before now. Now, the equation 3 here is what we are doing, what we use in modifying the conventional F. This equation 3 is a skewed form of distribution. You know, the reason why F distribution has a problem with outlier is because when you look at the genesis of F distribution, it's the ratio of two independent chi-square, and a chi-square is from the sum of square of a normal distribution. So whenever there's a violation, then it means we need to make F distribution to be more skewed. If you want to use that, this is a skew function suggested by F.C. Donald and Jones 2004. So it means we are going to put the PDF of F distribution and the CDF of F distribution into equation 3 so that we have a highly skewed F distribution. So this is a kind of a diagram. That F there is the conventional F, and other generalization that you can get from it. Now, equation 4 is the PDF of F distribution, equation 5 is the CDF. By the time you put it into equation 4, you arrive at this. This is what we call a generalized beta F distribution with 3 shape parameters. But we decided not to waste our shape parameter, we decided to use 1. So when b equal to 1, b equal to 1, this equation 6 becomes exponentiated F. So what we are trying to say, a single shape parameter is enough to bring things back to normality. Now, this is the Harrod moment of the distribution. If you make an attempt, if r equal to 0 here, everything will amount to 1. Because when r equal to 1 is 0, you expect that you have this figure. So this is the moment generating function of the new distribution. Then we look at the asymptotic limit behavior as x tends to infinity, as x tends to 0, what happened? So we realize that our new distribution has a mode. There is a cumulative density function of the new distribution. There is complete sufficiency of the distribution. We have it. Then we also obtain the other statistics as that. Then the entropy. Why are we interested in the entropy here? When outlier is in the data set, we discover that it will create what we call the degree of disorderliness. So what we try to do, we also want to cause the degree of disorderliness in the model, so that when the data is highly skewed, then the model that will capture that data should also be highly skewed. So we need to get the entropy here and the entropy, measure the entropy in the model. Then this is the critical region for the test. Now, we are done by developing a new distribution, and that will be used to simulate what we're going to have in our table. So we're going to have a robust F table. We will not be using the conventional F table. Now we are now back to the test. Here we try to look at the origin of the F test, and it is just the likelihood ratio of two normal distributions. If you look at equation 19, that is the F test, where you have the mean square treatment over the mean square error. This is the F test. Now the work we developed here, starting from equation 20, like that, then we have equation 20. Equation 28 is the exponentiated F test. This exponentiated F test is the one that we have developed, the one that is robust to any violation of absorption. When C equal to 1, what was introduced to the other one is C. When C equal to 1, then this go back to the conventional F test. Now, under the analysis of results, we decided to compare the performance of this proposed test with the classical F test by Fisher Ronald in 1935 and the existing robust test from it's called Smith, Bransford, and so on like that. Now, by trying to use 3 populations and 5 populations, and 2 at balance and imbalance, then what we decided to do, we set our nominal level alpha at 0.05. Now, when we use a Monte Carlo simulation, we simulated 10,000 times, and we actually want to compare the type 1 error rate. What we mean by type 1 error rate, that is how many times out of 10,000 do we take a very wrong decision. So if we set the alpha at 5%, if there is anyone that is more than 5%, then it has exceeded at 1 error, then there is a problem there. So if you look at the first table here, the first one there is classical F test, followed by the Welch 1951. Then the one we develop is in the last column here, where you see red. The red is indicating that the nominal level that we set has been exceeded, and that is the error. So you can see that in our last column here, we don't have anything like red. That is for balance design. The same thing occurs when we have 7, 7, 7, 10, 10, 10. Then when we talk about 5, when we have 5 populations, you can see there is no red here. Then for balance design, now where we notice error in our whole is in the case of unbalanced design. That is when you have 2, 3, 3, 0.1571. That is the only error in our own. Then if you go to unbalanced design as well, you will see that our own did not exceed the nominal level. So with what we have seen so far, then we discover that since we don't have a situation where our own is more than the nominal level, then we can actually conclude that the developed exponentiated F-tests outperform others. Now, in this work, we actually concentrated on one way ANOVA. Now, for study of further study, this can be extended to two-way ANOVA, RCPD, the Latin square, the Greco-Latin, among others. Now, then the idea of exponentiation can also be extended to when you are testing the mean in one population and in two populations, when normality assumptions are seriously violated. So, now, I said it the other time that the reason why the intervention, why people fail before now in solving the problem is that they still resort to conventional F-table. In this work, we're able, from the new distribution, we're able to develop a new statistical table for C equal to 0.1, C equal to 0.1, C equal to 0.2, and so on like that. Now, what is interesting here, when you get to C equal to 1, when C equal to 1, this is the table, this is the conventional table we have. So, what we are trying to say is that what Fisher did, Fisher made C to be fixed. But what we are trying to say here is that it can, in some situation, it may not be fixed. It can produce, it can proceed this way or this way. So, it can be less than 1, it can be greater than 1. These are situations where it is 1. Then these are situations where it's greater than 1. And so on, like that. So it is the data that will determine the value of C. And that C was the shape parameter that was introduced in this work. So, by references, thank you for listening.